Hi, my name is Tanjeen Ahmed, currently in my fourth undergraduate academic year at Wayne State University, studying mechanical engineering. I will be solving a heat transfer problem from the book Fundamentals of Heat and Mass Transfer, 7th edition. This problem can be found in Chapter 3, One-Dimensional Steady State Conduction. The course number for this heat transfer class at Wayne State is ME 4210 and is currently taught by Mahbub Islam. So to begin, this problem is a plane and composite walls problem. The problem states, the rear window of an automobile is defogged by passing warm air over its inner surface. If the inside warm air is at 40 degrees Celsius and the corresponding convection coefficient is 30 watts per meter squared Kelvin, what are the inner and outer surface temperatures of the 4 millimeter thick window glass if the outside ambient air temperature is 10 degrees Celsius and the associated convection coefficient is 65 watts per meter squared Kelvin? To start, we can call out everything that is given. So we have our inner warm air temperature here given as 40 degrees Celsius and the corresponding convection coefficient of 30 watts per meter squared Kelvin. The thickness of our window glass is 4 millimeters, and our outside ambient air temperature is negative 10 degrees Celsius, with the convection coefficient being 65 watts per meter squared Kelvin. And now what we want to solve for is the inner and outer surface temperature. Now using what's given, we can create our schematic to help solve for these two temperatures. We can consider this surface here to be our glass. And although not given, the thermal conductivity of glass is equal to 1.4 watts per meter Kelvin. On the right, we have our warm air. (40 degrees Celsius) with convection coefficient being 30. On the left, we have our ambient air. (-10 degrees Celsius) with the convection coefficient being 65. These arrows indicate what we are solving for, the surface temperature on the inside and the outer surface temperature. And our heat flux is going from right to left. And here is where our 4 millimeter thickness exists. Heat flux is defined to be delta T, or the change in temperature over the total resistance. Now we have our delta T given our warm air and our ambient air. So that can be solved for 40 degrees Celsius minus -10 degrees Celsius. In order to get the total resistance, we must draw an equivalent thermal circuit diagram, which I'll be drawing on the left side here. So to walk through this diagram, we have thermal resistance for convection occurring on the right side and on the left side, and thermal resistance for conduction occurring in the center. Now to solve for total resistance, our resistors are in series, so we can simply add. So 1 over 30 plus our length over our thermal conductivity, 0.004 over 1.4 plus 1 over 65, gave our total to be 0.051575 meters squared Kelvin per watt as our total resistance. Now that we have our total resistance, we can plug it back into this heat flux formula, and solving for a heat flux, we get 969.462 watts per meter squared. Derived from Newton's law of cooling, we have heat flux equals our inner convection coefficient multiplied by the inner temperature difference. Solving for this, we finally get 7.7 degrees Celsius as our inner surface temperature. Now using the same formula, we can also solve for the outer surface temperature. So my outer surface temperature comes out to be 4.915 degrees Celsius or 4.92 degrees Celsius. And that is all. Thank you for watching and good luck.